This video is a demonstration of the WebGrapher platform crawling a website and turning it into a live interactive graph of information. For this demonstration, we'll be using WebGrapher to build a comprehensive medical knowledge graph. Let's start by creating a new graph. Give the graph a name and a description and click Create. We're presented with an empty page. Let's click Crawl in the navigation bar to open the crawl modal where we can specify a URL to crawl. First, we'll need a source of information for our graph. An excellent source of information is publicly available by the world-renowned Mayo Clinic. Let's visit their website and explore the Health Library section. We can find a wealth of information, including diseases and conditions, symptoms, and test procedures. Let's go ahead and search for a disease such as diabetes and click on the search result. Here we can see the webpage about diabetes, a major chronic disease affecting hundreds of millions worldwide. Notice how the page has a title at the top and information about the disease underneath. Now, let's copy the URL of the web page into WebGrapher. And let's set the max links to crawl at 100, then click Preview to see what it finds. Here we can see the crawler microservice permitted the website to be crawled after checking the site's access policy and any rate-limiting restrictions imposed by the servers. The scraper microservice then proceeded to fetch the web page and store it in a cache. The normalization microservice then read the web page from the cache and extracted and normalized the data before generating a preview. Notice how the title and summary were automatically extracted along with some keywords and a list of top 10 tags for this page. It also found a large number of links to crawl, but many of these links are to navigational pages or irrelevant information. How can we improve on the accuracy of the information extracted to make sure what's found is related to the content? Let's click back. Notice the crawl form contains an advanced settings option. Clicking this expands the form to reveal additional controls. The URL filters lets us enter regular expressions to control which URLs are matched on a page. On the Mayo Clinic website, notice how in the address bar, the URL of the diabetes page contains the name of the disease along with a unique identifier. These are the only two values that change when looking at pages of different diseases. We can create a regular expression that tells the crawler to extract only URLs that match this pattern. This expression matches only URLs from the Mayo Clinic website that follow the exact structure disease conditions / followed by a single path segment, which is the name of the disease, followed by symptoms causes / and finally an identifier made up of characters other than /, question mark, or hash up to the end of the string. Now, let's generate a preview. This time, it found just 12 links to other pages. Notice how they match our expression exactly and how they are all diseases related to diabetes. Let's go back and configure additional options. Notice how we can also provide hints on where to find content on the page. For the title, we can provide an XPath expression to the HTML element that is the container of the title text. In this case, from the source web page, if we inspect the source code by right-clicking the title diabetes and selecting inspect from the menu, we can see the text is located inside the H1 HTML element, which itself is located inside the header element. Let's add this XPath expression to our form. This expression tells the crawler that our title text container is located inside the header HTML element and then inside the h1 HTML element. Now, let's generate a preview. Notice how the title has now been taken from the h1 element on the page. The crawler automatically extracted keywords from the entire content of the page. We can improve the accuracy by targeting only a section of the page to extract instead. This allows us to exclude things like headers and navigation elements that could potentially pollute the keywords generated. If we go ahead and inspect the source code of the page, we can see the main content is located inside an article tag with an ID of main content. And the text is located inside a paragraph element. Let's add these hints to the crawl form. All of the hints are optional, but the more we can provide, the more accurate the data and the more relevant the relationships extracted. The related links container is used to target where related links to information appear on the web page. In this instance, we will leave it empty. This will allow the crawler to extract all links from the entire body of the web page. Let's click Crawl and extract the information. Our graph now shows information about diabetes and related diseases. Let's see what other type of information we can add to our graph. From the Mayo Clinic website under Health Library, notice there's a section called Symptoms. Let's find the symptom. Let's select back pain. Notice the URL address of the web page follows a similar pattern to diseases. Let's create a regular expression for symptoms and add it to the crawl options. Notice instead of disease conditions, we have symptoms. Instead of symptoms causes, we have basics/definition. Instead of SYC, we have SYM, followed by the identifier to the end of the string. Let's copy the URL for back pain into the form so we can crawl the page. Now, this page has a slightly different layout from the previous pages, and the containers for the content and summary come from div elements with a class named page header. Let's add an XPath expression to our crawl form settings. For title, we will add a div with a class named page header. For content, a div with an ID main content. And now let's add the summary container. Let's go ahead and generate a preview. As you can see, we have extracted the title, summary, and keywords, and we have a large number of links that are all related to back pain. Notice how they match our regular expressions for both symptoms and diseases. Let's go ahead and crawl this web page. The back pain node is created and the microservices start crawling all the related links to other pages. We can see two separate node clusters forming. As more pages are crawled and their relationships are mapped in our graph database, we can see the clusters start joining together. Here they join on the disease acromegaly. Now we can see there is a relationship between diabetes and acromegaly, which has a symptom of back pain. Notice how other relationships between nodes related to back pain have been discovered by the crawler and how they relate to each other. Let's go back to the Mayo Clinic Health Library. Let's explore tests and procedures. Let's find and select the test procedure X-ray. Notice the URL of the web page. Again, it follows a similar pattern to the disease and symptoms pages. Let's create a regular expression for tests and procedures. This time we have test procedures followed by about, followed by PAC. Now let's copy the X-ray URL into the crawler and generate a preview. The title, summary, and keywords look good. The links contain the test procedure and a list of diseases related to the X-ray procedure. Let's go back and crawl the X-ray page. The X-ray node is created, and the other discovered nodes and edges start streaming into our graph. The X-ray procedure can be used to diagnose the condition carpal tunnel syndrome, which in itself could be related to acromegaly, which could be related to diabetes. We are also starting to see relationships between diseases and back pain that could be diagnosed with an X-ray. Our web graph of medical knowledge is really starting to come together, and the relationships between diseases, symptoms, and test procedures are working well. The health library at the Mayo Clinic holds a vast amount of knowledge. How can we make it easier to crawl all this data without user intervention? To demonstrate how we could do this, let's find another test procedure. Let's select MRI scan and copy the URL into our crawler form and click Preview. Here we can see a preview of the data and all the related links. We can take advantage of recursion and see the true power of our event-driven microservices by increasing the crawl depth parameter. Let's increase the crawl depth to 2. Potentially, if each page crawled had 100 links, we could trigger over 10,000 pages to crawl with just a single request. If we increase the link depth further, this could lead to over 1 million pages being crawled. Increasing it further substantially increases the number of pages that could be crawled. Not all pages will contain 100 links, but by increasing the link depth, we have the potential to crawl the entire medical library of information. Let's go ahead and crawl at a depth of 2. The crawler visits the MRI page and a node is created and streamed into our graph. Then, for each related link to a disease or symptom or test procedure, each of those pages are crawled and the data streamed into our graph. This continues until either we reach the link depth set in the form or there are no more links to follow. After a short while, we can start to see a comprehensive graph of medical knowledge that's been discovered from the pages we crawled. This is fascinating to explore. The larger nodes represent pages with a higher number of links or relationships to other nodes. Let's zoom in and explore in more detail. Notice how the directional arrows point to either incoming or outgoing links. Some nodes have edges with links in both directions. We can click the focus button in the sidebar to redistribute the layout if nodes become too congested. This explodes the nodes and redistributes them based on their size and forces generated. We can also use the sidebar to navigate, fly to, and explore other related nodes. We now have a complex medical relationship graph that we created with just a few simple clicks. What other information could we add that would really bring our graph to life? On the Mayo Clinic website, we can find world-renowned doctors and specialists. Let's find a doctor. Notice how the doctor's biography has a photo, summary, as well as links to other pages detailing his areas of specialization. Notice the URL of the doctor's webpage follows a pattern. Let's create a regular expression for this page. Notice how the image on the web page is contained inside a div element with a class named content image. Let's supply an XPath hint on where we can find the image on the page. Now, let's copy the address of the doctor's web page into the crawl form and generate a preview. Great, we have extracted the doctor's title, image, and summary. We can see the keywords generated and finally a whole list of diseases in which he specializes. Let's go ahead and crawl this page and leave the link depth at 2. As we crawl Dr. Ha, the relationship to conditions and diseases are discovered and we can visually see his areas of expertise in our graph. From the left side panel, we can click the focus button. This redistributes the nodes to create a more favorable layout. We can also easily explore the conditions he treats by clicking the links in the list. Let's go back to the Mayo Clinic webpage to find other doctors. Here we can browse a list of all doctors. This information is ideal to add to our graph. But look at the structure of the page. Only a small subset of data is ever shown, just 10 records at any one time. The rest is accessible only via paging controls or links to alphabetically sorted lists. If we click on a page or an initial, we get another 10 records of doctors. How can we extract the data without creating a separate node for each separate web page of results? If we look at the URL of the page, we can see it follows a pattern. The URL contains query string parameters that specify an initial of the doctor's surname and a page number. Let's create a regular expression for this pattern. Now, let's copy the URL of the Find a Doctor webpage into the crawl form and generate a preview. We found links to the 10 doctors from the search results, but no links to other pages of data were found. Our crawler by default excludes query strings from the URLs it extracts, but we can turn this feature off in the settings. At the bottom of the form is the option to exclude query strings. Turning this off will allow the crawler to include query strings when extracting URLs. Notice the Consolidate Query String option underneath. Make sure this is checked. This option allows the crawler to treat pages with varying query string parameters as a single node in our graph. This is the exact behavior we desire, as all doctors will be related to a single node that represents the Find a Doctor webpage. Let's go ahead and generate a preview. This time, the crawler has extracted paging links with initials B, C, D, the results of each of the 10 doctors, and also links to pages of results 2 through 5. The crawler will now be able to follow and crawl each of these pages and extract information for each of the doctors. If we set the crawl depth to 2, our microservices will recursively crawl each of the records, and the option to consolidate query strings will create a single node in our graph. Let's go ahead and set the crawl depth to 2 and click Crawl. As you can see, our doctors and their relationships to the data are being mapped and streamed into our graph. Clicking on a doctor's biography will reveal relationships to areas of specialization, tests, procedures, and symptoms. The larger the node, the more relationships have been mapped. Here we can see the single node that represents the Find a Doctor's page. This is the page with varying query string parameters that has been consolidated into a single node. Clicking the Focus button will redistribute the nodes of doctors across our graph and improve the layout. Notice how the source link would take us directly to the Find a Doctor webpage on the Mayo Clinic website. By consolidating all of the search results into a single Find a Doctor node, we can use this node to browse and focus on any of the individual doctors. We can click on a doctor's link to take us directly to that node. Clicking on a disease or condition will reveal a doctor's specializations in those conditions. We can zoom in and focus on nodes to fly to other areas of the graph. We now have an impressive medical knowledge graph from the Mayo Clinic. The graph includes their world-renowned doctors and practitioners and can also be used to browse and discover relationships to diseases, symptoms, and test procedures.